4 identical satellites, flying in formation, will travel through the most dynamic regions and the most active areas of our magnetosphere. What will they discover? What kinds of instruments will be used to explore magnetic reconnection? Find out on NASA Edge.
Welcome to NASA Edge.
An inside and outside look at all things NASA.
And a glimpse into an actual fully functional clean room.
I tell you what, Franklin, I was really excited about being in the studio today because it's been a long time since we've been in here. And as I walked down the hallway, I saw this yellow tape and this contraption, actually called safety, just to be on the safe side.
It's always good to be on the safe side and the clean side.
Well, I'm glad you are clean, but I wouldn't be alarmed. What happened is that over the past month or so, Blair and I have been running up 95 to the Goddard Space Flight Center to cover the MMS project.
Multi-scale mission?
The magnetospheric multi-scale mission. And we spent quite a few days in the clean room with the satellites. And Blair, I think, to, be one with the MMS mission, decided to put together his own clean room.
Yeah, it's kind of like what I like to call FPI magnetosphere. Kind of like CSI, crime scene investigation. Well, MMS is doing fast plasma investigation, which is actually almost like a crime scene in our magnetosphere.
How long did it take you to build this contraption?
A long time, actually. It's very important to get all the parameters correct so you can be 100% clean so none of these important instruments are damaged in the process. And actually, I really need to get my positive pressure system going here.
Well, Chris, since you weren't with us on this last show, why don't we watch an interview that Blair did with project scientist Tom Moore on the MMS mission so that you and our viewing audience can find out a little bit more.
Hey, let's go check it out.
And when we come back, I'll probably have some instruments in here and begin work in earnest.
Oh, yeah, here you go. That's yours.
You can't do that. It's got to come in its protective bag. Tom, it's really exciting to see the progress on the spacecraft here in the clean room. But my question is really, what exactly are these spacecrafts going to do once they're actually flying in space?
I think a good way to think of that is if you remember back to the movie Twister, where the scientists release a whole bunch of probes up into a twister and they work really hard to try and get them located just in the right place so they'll actually get transported up into the core of the vortex. Well, we've spent all of our time planning the orbits for the MMS spacecraft so that they'll essentially land right in the middle of the biggest twister going on in geospace, which is the reconnection sites of the upstream and the downstream sides, so that they can make key measurements, tell us what's going on in there.
When we think about the twister analogy, we think, well, that research helps us understand storms better so our houses don't get blown down. How is MMS helping us based on the information it will get from this mission?
We're going to be trying to learn the things we need to know to understand when our spacecraft are going to get blown up.
Our cruisers can't repel firepower of that magnitude.
We have problems where spacecraft will be subjected to energetic particles that either make their circuits misbehave or even disable their circuits at times. So we want to be able to understand when those storms are coming and predict when they will affect spacecraft that are inside the magnetosphere. And all the connection of solar space weather to the interior of the magnetosphere is through reconnection at the boundaries of the magnetosphere. So by studying reconnection, we're studying the one word that's been used recently is portals, by which the energy gets from outside to inside and makes a difference in the conditions for the satellites that are in space orbit. We have many thousands of satellites. It's kind of understanding, too, when our systems misbehave, do we have to be concerned about their health for the long haul, or are they just misbehaving because of a storm that's going on that day?
And has this been done in the magnetosphere before?
Well, there have been other spacecraft that have flown through those same places. We know they're there, we know that we're going to see them also, but we haven't had the kind of measurements that can actually see what's going on in there. What tends to happen is there's a very thin layer, if you will, the vortex, and it tends to whip by the spacecraft so quickly that they don't really get any measurements of the twister itself. They see what's coming, they see what's left after it goes away, and they miss the main show. So the MMS spacecraft are designed with video frame rate resolution so that we get very fast measurements. And even if it goes by so quickly that it's only there for 1 second, we'll get mini measurements of what was going on in there.
How do you capture that kind of data of what you would call a magnetospheric storm in space?
Well, you have to pick and choose your instruments carefully, and there had to be some huge innovations over previous instruments. You know, the things you want to measure in there are not that different from in a real tornado. You want to measure the pressure, and you want to measure the temperature, and you want to measure how fast the winds are circulating, and you want to measure the composition, perhaps, of the gas in there, see if it's different. So in order to do that, we had to have a lot of sensor heads all around the spacecraft so that we could look at the whole sky without waiting for the spacecraft to spin. Historically, our spacecraft and instruments have used the spacecraft spin to scan the sky, and therefore you're only looking one place at one time, and it takes 5 or 10 seconds to scan the whole sky. Now, we have 8 sensors going parallel. We'll snap the whole sky in a 30th of a second.
In addition, you also have multiple spacecraft taking pictures of the same spot from different angles.
That's right, and the boundary itself will wash over all of the spacecraft, most likely in a given pass with it. So we'll get 4 different looks at it in different locations and at different times, be able to put together the story of not only what it looked like at an instant, but how things are developing in there, changing with time.
See, Chris, Tom gave us some good scientific insight and overview of the MMS project.
I tell you what, he sure did, and I have to give Blair some props for the great interview. It's actually a pretty cool mission after listening to it speak, and the thing that actually struck me is that this is actually, the magnetosphere is actually the final governor for space weather, and it's really that reconnection that causes all those geomagnetic storms, the GPS systems going out, the electrical grids, the communication systems, and with this mission, you're actually going to be able to study that and how that affects our satellites.
Yeah, and I thought the twister analogy worked.
Good movie.
Yes.
So now I'm getting emotionally attached to my satellites, and I'm thinking, I don't want them to go into this storm-like area. It's kind of frightening, because just like those little sensors, they're going into that very dangerous area with the hopes of saving other spacecraft. So that's kind of a really nice touch to their mission.
Blair also talked to another gentleman by the name of Ken Shelton, who gave us a lot of insight on the fast plasma instrument suite, which consists of the DES, which is the dual electron spectrometer, and the DIS, which is the dual ion spectrometer. And it was really, really interesting to see how those spectrometers on all 4 satellites work in concert with one another to give us the type of images and data that they want to get out of this mission.
So in the instruments, all 4 spacecraft are going to have identical instruments in all 4.
Identical.
Identical.
And I'm telling you, it's important because as I learned when talking with Ken, it's really important to replicate that data across a broad spectrum, and that's what it's doing. The amazing things, and I haven't gotten to it yet, is this IDPU, the instrument data processing units that allow this complex processing to take place. It's kind of a big deal.
I tell you what, let's go and see that interview with Ken Shelton, and when we come back, we'll talk a little bit more about it.
And I'll try to find it on my model.
Hey,
here.
my cousin Vigi.
Yeah, very good. So great. Now, we're in the electronics lab. What's actually taking place with the instrument right now?
Well, Blair, at this stage in the project life cycle, what we're doing is we're taking the 3rd of the 4 total that we're delivering, and we're doing a set of EMI, electromagnetic interference and compliance testing, to be sure that the instrument doesn't emit any radiation within the spacecraft that would interfere with any of the other instruments. And there's requirements set by the MMS spacecraft that says there should be certain frequencies at certain magnitudes that should come off the box, and anything greater than that could be a problem with one of the other sensors in the MMS mission.
And so far, so good. Everything's looking good.
Oh, absolutely. So far, so good. Everything's passed. We haven't had any issues that we couldn't overcome.
Now, there's some other things about the instrument itself that's kind of interesting. This fast plasma instrument that the IDU is part of, it seems like that might be the brains of the operation. Is that true? What does it exactly do?
It processes the data that the sensors receive. In addition to, it commands the spectrometers, the dual electron spectrometer and the dual ion spectrometer that make up the FPI instrument. So the IDPU commands the instruments, and it also takes the data that's received from those instruments and processes them.
So those instruments, the DIS and the DES, are the ones getting the information out in space, right?
Absolutely.
And then the IDPU is sort of capturing that data.
It takes that data, it processes it. It does a couple different things to it. You know, one of the things that it does to the data, it despins the data, right?
Oh, despins it. That sounds cool. What's
Right.
that?
What despinning means is as a satellite is in its orbit, it actually has a natural rotation to it based on the physics of the actual mass that's in space. And so when these sensors are collecting data, they're collecting data as it's spinning. So what the IDPU has to do is despin that data so that we can put all the information in a relative position to a given point on the spacecraft, which we call the sync point, which tells us when a certain part of the spacecraft is facing the sun.
Okay.
Okay, so from that reference point of that part of the spacecraft that's facing the sun, we despin the data so that we know in relative terms where we collected this data from. So that's one of the things that the IDPU does.
That's kind of like the Rand McNally flat map of the Earth, right?
Of the Earth, absolutely.
Yeah, so like that's a despin picture of
the Earth.
of the planet. So you despin the data that the MMS is getting.
Right, that's an excellent analogy. That's exactly what it does. It takes the data that's being acquired by these spectrometers and we flatten it out so that the scientists can know in relative terms where does this data come from. So that's one of the things the IDPU does. And also it compresses the information. Since these spectrometers collect so much data, in order to process it to a packet size that can be transmitted in an efficient way, we do what we call data compression of the data.
Okay.
So we grab all this data and we compress it in a format that's small enough that we can transmit it down to the Earth. And then once the data is received on the Earth, they can decompress it if they want to, or they can look at it in compressed formats. We store everything, but we only download certain things based on what has been deemed of interest at a given time. The IDP will have certain parameters built into it, which are the default parameters, if you will. But if during the mission they decide that they want to change those parameters, the ground support station can upload packets or routines that allow them to modify and adjust what a trigger data term, what a trigger data number is. So they can change these things on the fly if they
That's
need
like a
to.
firmware update. You can decide.
Exactly.
You
I mean,
you wanna
another
look
good
at-
analogy. It's just like an update to the firmware. Yes.
Well, that's cool because that means if you do learn something, you can actually recalibrate on the fly to get even better scientific data.
Absolutely. You know, you don't want this to be a static mission. I wouldn't imagine. I mean, from an engineering perspective, I wouldn't want the hardware to be a static piece of hardware. I want it to be very dynamic, very programmable, almost autonomous, if you will. But we also give the actual scientists the ability to adjust and modify the profile so that they can determine what data they receive when.
One of the biggest challenges I think that MMS faces is the amount of data that they collect. It was really interesting that Ken was talking about the kind of brains, the motherboard, that IDPU that each MMS has to handle the heavy volume of data that's coming down. And not only just handling the data, the volume, but being able to extrapolate it out in a usable form for the scientist.
And I'm sure that's for all instruments that are on the spacecraft, not just the ones that Ken's working on, right?
Sure. And his is sort of like that throughput, the kind of the distributor, if you will, for all the data. So it's kind of, they all work together, obviously, but what a task they have, and as they're going to be crunching a lot of numbers.
Well, Blair, can you see the DES or the dual electron spectrometer and the dual ion spectrometer on your Lego?
Yes,
MMS?
actually I can, but I'm having a hard time getting to it. But yeah, they're here. Very important.
Well, I actually stood up and talked to Ulrich Glees, who's working with those spectrometers. So let's look at his interview and come back on the other side and talk about what he said. Ulrich, we're sitting here with what they call the engineering test units of both the DIS and the DES.
These are two of the instruments on the MMS mission. The DIS, which is the dual ion spectrometer, is built in Japan by a company called Meisei. And the DES, which is the dual electron spectrometer, is built here at Goddard.
Exactly how does the DES work when it's flying on MMS?
So both of these spectrometers are dual spectrometers. As you can see, we have two things that look the same up front here. Those are what we call the sensor heads. So each of these two sensor heads is kind of an independent sensor that is then sharing the rest of the box here. So when the electrons or the ions flow through space, they will hit the instrument from a certain direction with a certain energy and with a certain rate. and that's what we are trying to measure. So number one, where are they coming from in space? So this instrument can look out 180 degrees in that direction, and it can look out -22 and +22 degrees in that direction for each sensor head. We can set the instrument such that it determines what energy the particles are coming with, and then we're counting how many particles that are coming in per second into the instrument. And in that way, with having this instrument and 4 of them on the spacecraft, we can measure electrons coming from the entire 360 degree of the sky hemisphere.
As I said when we first started, these are engineering test units, but these are not the flight units.
That's right. It's not a mock-up, but it is our initial design unit, so it's pretty much exactly like the flight unit. There are slight differences, right, because you built this unit to find out whether the design works or not. And you will find some things that don't work as you expected, and then you have to modify it. So these units have gone through various modifications of the electronics inside and of some of the mechanics and so forth. So you get it to the point where, yes, now you know that it works, right?
How different are the spectrometers that have been built before to measure electrons?
Yeah, so these instruments are very similar to what have been done before. There are two things that are new to this mission. And number one is the rate at which we're measuring. So we're measuring every 30 milliseconds, so that's 30 times a second. We're taking, if you will, a snapshot of the entire sky around the spacecraft. So that produces around 16,384 data points every 30 milliseconds. So 30 times a second, we're producing that many data points. So that speed is about 100 times faster than what has been done before. So that's one thing that is new about the mission. And to do that, we need to have a lot of instruments. So one of the biggest volumes that has been built before was on the Themis mission, where they had 5 instruments, and they had an electron sensor head and an ion sensor head on each instrument. On this mission, we have 32 electron sensors and 32 ion sensors. So that's another thing that is very different, is the volume of instruments built. So we're building 16 of these boxes and 16 of these boxes, which is a large volume here at NASA.
Hey, I tell you what, Franklin, that was a pretty cool interview. Just seeing all the instrumentation that goes on to MMS spacecraft.
Ulrich told me a lot about the DIS and the DES.
How do you remember all that?
But you know, I don't say it all the way through. Like the dual ion spectrometer, man, that's like saying it 5 times fast.
Right.
But Ulrich really gave us some good insight as to how the magnetic reconnection will have an effect on the MMS satellites. And when they fly through, how those sensors or those spectrometers will capture the ions and electrons passing through there, and how they will be able to get a snapshot of exactly what's happening during that phenomenon called magnetic reconnection.
It just blows me away, the fact that you can have a team of scientists and engineers developing this instrumentation to fly through the magnetosphere of the Earth. You can't see anything. It's invisible to us, but yet they're going to be able to come up with a 3D representation or a model of what's going on in the magnetosphere. And you talk about that reconnection, where that energy transfer, between the Earth's magnetic field and the sun's magnetic field. I mean, it's unbelievable.
It's virtually a festival of fast plasma investigation.
Hey, I tell you what, MMS Education Public and Outreach Team came up with a pretty cool bookmark that you can download. And on the back side, they actually have a QR code that you can use if you have a QR app on your phone or a mobile device, and you can learn all about MMS, which is it's a great way for the public to learn more about the mission.
And it's a very huge team, great team of people that come together. And
no, breach. Oh, that's bad.
What'd you do?
Oh man, I need some tape.
Hey, while Blair deals with his dirty room, we're going to take a look at an interview I did with Art Jacques, who will tell us about the MMS team and what they had to do to get this mission off the ground. Dude, that looks like I'm looking through a dirty shower curtain. There's a significant international partnership with this project. How difficult or easy is it to manage a program like that?
It's a challenge.
Okay.
In my career, I've never had this level of challenge. If you can think about it, you're managing teams that are 13 hours difference in time zone. They're in Japan versus in the United States, and then there's the linguistic challenges. And then you add to that the challenge of managing the interface between the French and the Japanese to make sure that hardware is delivered on time. It all revolves around good communication. So we meet with the Japanese once a week, we talk with the French once a month, and we're always engaged on a daily basis when they're testing hardware as required. It's all about being a team, and the analogy of a football coach is a very good one. If you think about one instrument, for instance, and running it through an environmental test program and using facilities here at Goddard, that can be a challenge. You're competing with other programs and you negotiate those things up front. But when you're managing 16 instruments and then 4 data processor units, you're always finding competition from other programs for the very facilities that you need. So I have to not only work with my team on FPI, but I also have to work with other program managers on other hardware. Even MMS, for instance, the electronics that goes on the spacecraft bus has to use the very same facilities sometimes that we use. So it's always about negotiating and setting priorities, and I don't always win. So you have to give sometimes in order to help people meet their priorities, and then they have to give sometimes to help me meet mine.
Talk a little bit about getting the DIS from Japan to the United States, or vice versa.
That's a really fun aspect of the job, because we have to physically go to Japan and take delivery of the instrument. We have to get it through customs in Japan, and we have to actually get a seat on an airplane for not only the individual transporting the hardware, but then the instrument itself. So for all 16 instruments, we have to have people fly to Japan, review the data products, accept the data, accept the instrument, and then import it, bring it in through the States. And then we have to go to Huntsville, Alabama. Marshall Space Flight Center is another key integral part of our team. They do the calibration of the Japanese instrument, and they make sure that it meets its performance requirements before we take delivery at Goddard and then integrate it to the spacecraft.
Now, you know what I'm thinking about right now?
Yes.
The instrument gets a seat on the plane.
Yes.
How do you write that up on your passenger?
On the expense report? Well, the nice thing is you get to board early, because they treat you as if you have a child or someone who needs special attention. So that's the one benefit of having an instrument delivery. But you have to physically get on the airplane before everyone else, because this is a delicate instrument and it can't just be jostled around. You have to carefully put it in the seat.
Window seat?
Sometimes, yeah, it's a window seat. I get the aisle, the instrument gets the window. And so there's that complexity of transport, but you have to handle these things delicately because they're very sophisticated instruments.
All right, Franklin, I have one question.
Mm-hmm.
Who gets all the frequent flyer miles?
You know what? NASA. I think that's the way we're going to get to space.
I mean, they could move the love over here to NASA Edge and give us the frequent flyer miles.
My new name is DES. I wouldn't mind a ride to space. Of course, now that my clean room activity is kind of shot.
That's not a clean room. That's a clean booth.
Well, that's not bad. Look, it works. It doubles as a mosquito net.
Well, the only thing I have an issue with is that they had such a strong team for MMS, or they do have a strong team, but you're a team of one. And you notice that for 4 satellites, they have a lot of people working on it.
Well, I clearly need a few extra team members inside the clean room and down the production line. But
okay, but you work on that.
Yeah. I mean, you live and learn. I mean, this is what science is all about.
Okay,
right?
Sure.
Yeah.
All right. Well, I'm going to collect these parts and see what happens, and hopefully we can salvage this and maybe get something workable. Me and my team.
Hey, tell you what, we're looking forward to the launch of MMS, which is going to happen in October of 2014. So we're going to be live down at NASA Kennedy. Hope you can join us on board an Atlas V.
We're going to be on an Atlas V?
You're watching NASA Edge, an inside and outside look at all things NASA and MMS.
He said we were going to be on an Atlas V. I thought you said we would be on an Atlas V.